Good morning, everyone. Today we are going to start Unit 7, and we're going to talk about the mole. So the first question you see on your note sheet is, what is a mole? By the way, this note sheet is in your packet, should be the very first page. So we'll be filling this out together, and we'll be going through this note sheet in the back of it over the next few days. So like I said, the first question is, what is a mole? A mole, I know we think of a mole as a little animal in the ground or a mark on your skin, but in chemistry, a mole means an amount of something. So in the same way that we use words that mean a certain number, so when you are talking about going to the store to get 12 eggs, you say, I'm going to the store to get a dozen eggs. Or if we're talking about how many years is equal to a century, we are referring to 100 years. So we're just referring to a certain number when you say the word mole. It's an amount of something. What do we use the mole to describe? We are normally talking about particles, specifically atoms or molecules. So it's an amount of something. It's used to describe particles. And those particles are atoms or molecules. So the next question is, who is Avogadro? Because you'll see in a minute, we're going to talk about the mole as equal to a number that is called Avogadro's number. So who is Avogadro? Why is this number named after him? Avogadro was an Italian scientist who first proposed that the volume of a gas is proportional to the number of atoms. So in other words, he made some discoveries while studying gases about how their number, the number of particles present, is how it relates to the volume of that gas. And all of this has to do with the word mole. So we name the mole what it's equal to after Avogadro's number. And that number is equal to 6.022 times 10 to the 23rd. Now, if we did not write this in scientific notation, imagine that after we move the decimal after the 2, that we then add 20 zeros after that. So this is a very, very large number, and we don't want to write all those zeros, and that's why we write this in scientific notation. Now, you probably don't really grasp how big this number is just by looking at it. So I want to give you an illustration that hopefully will make a little bit, will give you a visual at least. So how big is a mole? If you had a mole of $1 bills, so let's say you had 6.022 times 10 to the 23rd dollars, and you were spending that money at a rate of $1 billion per second, how long would it take you to spend that much money? So again, this number that we're talking about, 6.022 times 10 to the 23rd, if you had that much money and you were spending it at a rate of $1 billion per second, how long would it take you? And you can see on this poster, it would take you 19 million years to spend all of that money, even if you were spending it at such a high rate. So obviously, you wouldn't be able to spend that in many, many, many lifetimes, let alone your own. So this is a huge number. So why are we talking about such a big number in chemistry? It's because atoms are so very, very small. you cannot see atoms. So if we're talking about a bunch of atoms, if we want to talk about enough that you could see it, we got to talk about it in terms of moles, millions and millions of atoms. Okay, so on to the next question. What is the molar mass? The molar mass is the mass of 1 mole of a substance. And the unit we're going to use for that is grams per mole. By the way, the abbreviation for mole is just to take the E off the end. I know. They really saved us a lot of time there. Now what we're going to do is we're going to look at that periodic table that we've been using a lot this semester. Hopefully you've got your own personal copy at home. Funny enough, I actually don't have a physical copy of one, so I've saved this image to my computer. But you can also, if you don't have one, you can go online. There's a great website called the Dynamic Periodic Table that I would encourage you to use if you don't have one. But if you remember from the beginning of the year, we talked about how in each of these element symbols, there are 2 important numbers. There's the atomic number that tells you the number of protons an atom has, an element has, and that number is the identity. It is, you can think of it as the DNA of that element. The other number you see here is the mass, the average atomic mass. Now, something you should know is that we are not saying, and I'm looking at boron right now, we are not saying that 1 atom of boron weighs 10.8 grams. That wouldn't make any sense because a gram is about the size of a small paper clip. So if you had 11 small paper clips in your hand, you could see that. We can't see 1 atom of boron. So the connection I want to make here is this 10.8 that you see here, this is the mass of a mole of boron atoms. So if you had 6.022 times 10 to the 23rd atoms of boron, those would weigh 10.8 grams. Okay, so that's why it's called the molar mass, the grams per mole, because this is how many grams a mole of boron would weigh. All right, so you'll notice that the next question on your sheet says to find the molar mass of sodium. All you have to do for that is to look at sodium, find it on the periodic table, and write down the molar mass. Now, since it's 22.99, I'm just going to round that up to 23 grams per mole. And you'll notice, or you might want to make a note next to this, just look at the periodic table. All right, the second question, finding the molar mass of a compound. So it's pretty easy to find the molar mass of an element. You just look on the periodic table. But what if you have a compound? So this is sodium carbonate. So you have 2 sodiums, 1 carbon, 3 oxygens. How would you find the molar mass of that entire thing? Well, you might have already guessed it. You would take sodium's mass, multiply it by 2, and then you'd have to add it to the mass of 1 carbon and 3 oxygens. So I'm going to show you how to set that up. I've got sodium, carbon, and oxygen in this compound. How many of each one do I have? Well, there's a 2 next to sodium. There's nothing next to carbon, so that means 1. And there's a 3 next to oxygen. So now I'm going to multiply each of those by their molar masses. So we know from the previous problem that sodium's molar mass is 23. Carbon, scoot this over so you can see. Actually, it's not letting me scoot it over. There we go. So I'll look here for a second. Carbon's molar mass is 12. We can just round that to 12. And oxygen, you can see oxygen, 15.999. We can round that to 16. So if you multiply each of those out, you get 46, 12, and then 48. Now we add them together. So 6 plus 2 is 8, plus 8 is 16. 1 plus 4 is 5, plus 1 is 6, plus 4 is 10. So it's 106 grams per mole. All right, so you can see you're going to be relying pretty heavily on the periodic table for this unit because we've got to look at those molar masses. The next thing I want to show you, and if we were together, this would be an activity that we would do. I would have you go to the lab and you would each have a block like you see here. Now, if you read each of these blocks, it says 1 mole. Each of them say 1 mole. And the first thing I would have you do when you go back is identify what element each of these blocks are made of. And in order to do that, you would have to put this on a scale. So if you put this block on a scale, the mass would come up, and you know that since this is equivalent to 1 mole, you would simply look at the periodic table and identify what the element is. Now, the second question I would ask you is how many atoms are in your block? So once again, the fact that this block represents 1 mole means that there are 6.022 times 10 to the 23rd atoms in each of these blocks. Now, you might notice each of these blocks are different sizes, and they also are different weights. They're different masses. And that's because not all elements have the same number of neutrons, the same number of protons. So we have the same amount of atoms, but we have different weights. And that is why they're different sizes, and some feel heavier than the other. Same amount. It would be, just to give you another example, it would be like if you had 12 elephants versus 12 mice. Which would you expect to be bigger and heavier? The elephants, because there's more mass in an elephant. But you still have 12 elephants versus 12 mice. So it's the same thing here. The amount or the number is not identical to the mass. All right, so what you're going to do now, you're going to do a lot of practice problems. In your packet, you're going to be doing page 2. And it's just a lot of problems of solving for the molar mass, just to make sure you're comfortable with doing this. So let me know if you have any questions, and I hope you have a great day.